Thank you. So I did put first some of the slides from yesterday just to remind. You remember we wanted to classify regular inclusions, regular subalgebras of the hyperfinite one, but in the sense of inclusion, so the isomorphism class of this, so that's what we want to classify. We impose this condition always. It's really, very natural. So this is something you'll always kind of assume for such this type of problem, this relative commutant condition. Okay, the relative commutant of the subalgebra should be included in B, meaning that it's equal to the center. And so we've already done it, right, of course, for the case B abelian, where regularity, this condition amounts to B being a massa, and a regular massa is what we call the Cartan subalgebra. We did that, that's Kohn-Feldman-Weiss. The next, of course, case of interest is when B is a subfactor, and then this condition amounts to B, which when it is a one factor, I generically call it N, when N has trivial relative commutant in R. Okay, and I said that then, the normalizer divided by the unitary group of N, that will be a countable group, it's very easy to see, and amenability of the ambient algebra of M translates into this, implies that this group is amenable. Also, this normalizer really, this situation, the regular inclusion, the fact that the inclusion is regular amounts to this, the algebra. You remember this was from one of the previous pages. Actually, we'll get back to that. It amounts, so if N is a subfactor which has trivial relative commutant in another factor, this doesn't depend, of course, on the ambient factor being R, with trivial relative commutant and regular. So as I said, you have this normalizing group, and in fact M will be a cocycle cross product with this group. Okay, so this is a general fact, and it's very easy. It's an observation. And so for regular subfactors, the answer is given by Ogneanu's theorem. So irreducible inclusions are completely classified by that into R. Irreducible regular inclusions. Okay, so subfactors, trivial relative commutant, and regular are completely classified by their normalizing group. So this group that I said before, the normalizing group, is, of course, it is an invariant, that it's a complete invariant. In other words, if N0 is another such subfactor, then the two are conjugated by an automorphism of the ambient factor R, if and only if these groups, the corresponding normalizing groups, are isomorphic. Of course, you can also view it this way. Since you always have for a group gamma the Bernoulli action, this amounts to saying that any kind of inclusion like this with gamma normalizing group is isomorphic to this special inclusion, which we view like a model inclusion, which is this, okay, N into N cross product gamma, where N is the hyperfinite one factor in this representation, and the action of gamma is the Bernoulli action. Okay, so this is kind of nice to emphasize it this way. So all this brought into attention this situation with this normalizing group, which gives rise to a cocycle action, in fact, on n. And so we started the whole discussion about arbitrary cocycle actions. I reminded you what a cocycle action is, pre-cocycle actions. Then I emphasized these two. You will see why. Okay, so I meant to put, though already last time, to put up this. To give these two examples of cocycles that, you know, are not at all obvious that they could be untwisted, that they are, well, I guess here is not yet the definition of what we mean by vanishing of the untwisting or such a cocycle being coboundary, but we'll see that soon. I just gave immediately two examples of cocycles and cocycle actions more precisely. This is the so-called Kohn-Jones cocycle and these amplified cocycles. So they, just to show you that they come up naturally in you know, lots of situations. And I emphasized also that cocycle actions, you can construct for a cocycle action the cross product for Neumann algebra exactly the same way we did it for genuine actions. I remind you that when the action is, so this we did, you know, and also on the previous page for arbitrary, for cocycle actions on arbitrary threshold for Neumann algebras, but let me remind you that when you act on a II1 factor, the freeness, well, in general, freeness amounts to this condition: B prime intersected M is the center of B, and in the case of when acting on a II1 factor, that amounts to N being irreducible, having trivial relative commutant in the cross product. Okay, so in other words, when you have a cocycle action on a II1 factor, you have that gives rise to a cross product algebra with the subfactor n naturally sitting in it, okay, and it's regular in it, obviously. And here I emphasize that you have conversely, when you have an irreducible regular subalgebra, regular inclusion of factors, then, you know, this normalizing group actually implements, if you denote it by gamma, it implements an action on, a cocycle action on n, and you can view this inclusion as n into n cross product with this cocycle action with gamma, I mean identifying m in that manner as a cross product algebra. Okay, so you see this is, yeah, how this correspondence, so it shows you that you have like a complete equivalence. Of course, in fact, I think I mentioned that on the next page. Yes, yes, exactly. So here I mentioned that two cocycle actions. So first of all, what it means for them to be cocycle conjugate. I guess here I wanted to correct. Masaki pointed out that I have to add of Wg. I forgot the Wg. So, okay, so it's an add of the Wg here. Okay, so these two axioms. So there exists an isomorphism of the ground spaces that intertwines the action modulo some inner perturbation of one of them, and with the cocycles, you know, going from one to another in this way. And this is the point I wanted to make. So two pre-cocycle actions on to one factors are cocycle conjugate in this sense if and only if the corresponding inclusions are isomorphic. Okay, so you have these two categories basically with corresponding isomorphism between objects which are kind of equivalent, okay? The cocycle actions and respectively inclusions, the associated inclusions. Okay, so the untwisting means that, or two cocycle means this, that you can find a one variable unitary valued function on gamma such that the VGH is the delta, I mean the derivative sort of, yeah, the co-boundary of this WG. So I emphasize that this is more, right? It's a stronger condition than just the fact that this is becomes a genuine action. It says this, but it says more. So it is this thing, which is more than, you know, just saying that this becomes a genuine action. If you look in the cross product thing, you know, it really is equivalent this to saying that you have a perturbation of the canonical unitaries which give you a representation of the group, a gamma representation, actually a copy of the left regular. Okay. And just to give you an example, I wanted to put this up very quickly because, you see, this is a non-amenable group that, you know, has no cohomology whatsoever. So we'll see, because, you know, this is to keep in mind all the time, because we'll talk about untwisting cocycles for amenable groups. It may make you think that, you know, it's specific for amenable groups, this untwisting of two cocycles. Well, it's not, okay? So the groups, I mean, there is one very non-amenable group for which you have no two cocycles in some sense, right? Okay. I think we were more or less here. Okay, so I'm sorry I lost this 15 minutes, but we needed to recall a little bit the context. So I stated Ogneanus' theorem in that form that gives the classification of regular subalgebras which are factors with that condition, which becomes then irreducibility, subfactors of R. Actually, it's not the original statement of Ogneanu. His theorem simply states that any two free cocycle actions of a countable amenable group gamma on R are cocycle conjugate. But as we have seen, that's equivalent to that formulation, okay, for inclusion. Now, this result was already known, so this is the way things happened historically. It was Kohn who proved it for gamma, basically for automorphism. So he classified all automorphisms, periodic or aperiodic, of the hyperfinite II1. There is more into this story because there is also an H3 cocycle, which is an invariant. I don't want to get into that. So we just take actions, free actions of groups, in particular in this case of Z over NZ. So that's how, yeah, okay. And so in that case was Kohn, and that was a very strong motive. I mean, of course, it's great and interesting to classify automorphisms of the hyperfinite one. After all, you know, this is an obvious, you know, sort of dynamics, non-commutative dynamic that is, you know, obviously interesting. So we passed from the unit interval, which is the standard probability measure space in classical dynamics, now to a non-commutative unit interval, which is our hyperfinite one. The first thing you want to look at, you know, I mean, one of the first things is to look at its symmetries, its automorphisms. And this was a big deal for the probability measure space, ergodic theory, dynamical system, etc. I mean, measurable dynamics. Well, so one would obviously like to see it here, and as it happens, it's an extraordinary problem. Already there is something which we will not touch in these lectures at all, which is that besides your sort of usual notion of symmetry, which I would say that's an automorphism, you have what one could call quantum symmetries, which are endomorphisms of finite index. Well, to make it short, it's the whole Jones theory of subfactors. Okay, so that's what can be viewed as the studying generalized symmetries of the hyperfinite one and more generally of arbitrary one factors. It's an extraordinary rich subject and very actually complicated and hard and with lots of fantastic things happening. But we don't go into that, at least, I mean, at some point we'll have to comment more on subfactor theory, but not going too deep into it. So, as I said, moreover, in fact, Jones proved also that any two free gamma actions on R for a gamma finite are in fact conjugate. Okay, and also Kohn in fact proved it for Z over NC that any two periodic automorphisms are actually conjugate. Cocycle conjugacy is same as conjugacy because one cocycles are co-boundary. Okay, so that's actually, it's like saying this. Okay, so that's on the one hand. I also want to emphasize that since, so Ocneanu proved this uniqueness theorem, right? So any two cocycle actions are cocycle conjugate. Now any group has an actual action on R, which is by Bernoulli shifts, right? So since you take now any other cocycle gamma action, it will be cocycle conjugate to this genuine action, so that means that any cocycle action untwists, any two cocycle untwists, right? Because it's cocycle conjugate to an actual action, right? You remember the definition, and we emphasize this fact, okay? So his result also says that any cocycle, any two cocycle of a cocycle action untwists, is co-boundary. Let's keep that in mind. So now, yeah, just getting back to the initial formulation, since gamma is amenable, the cross product of R with, I'm getting back of why this implies the other, okay? I mean, just pointing out that, of course, you use Kohn's theorem, because you get that the ambient, the cross product factor is isomorphic to R, so you are dealing with subfactors of R here, right? Okay, so that's, okay, so in particular, okay, one more time. Ocneanu's result shows that any such irreducible regular inclusion N into R is a true untwisted cross product, okay? Coming from a genuine gamma action. Actually, I put it also at the end of the formulation of, in the first page of this. Okay, so I was thinking to give a sketch of the proof of Ocneanu's theorem. So there are, so the proof he gave is, quite involved because it really goes the hard way. What happens, I can explain you a little bit of two things that were, very important. One was the Ornstein-Weiss theorem that we talked about, with the actions on the probability measure space, and of amenable groups being orbit equivalent. Now their proof is not, I mean, what I showed you as a proof was the Kohn-Feldman-Weiss, which is stronger, okay, theorem, and you remember with the little local finite dimensional approximation, etc. So, however, the Ornstein-Weiss theorem, which appeared a year before Kohn-Feldman-Weiss, so this is how things happen. So Ornstein and Weiss proved that result, and then Feldman and Weiss started to think more towards, you know, proving that any equivalence, amenable equivalence, abstract amenable equivalence relation, so not necessarily coming from a free action of an amenable group, you know, also was giving you this unique amenable groupoid amenable equivalence relation. So which amounts, you know, to this uniqueness of the Cartan, but without the two-cycle vanishing. So they discussed with Kohn, and then together the three of them, you know, proved this. As it happens, the proof is very, it's basically what I showed you, so it's identical. That's the proof they gave, you know, with this local approximation. So this is what inspired me to build the proof of Kohn's theorem in those years. But it's really their proof, okay, Kohn-Feldman-Weiss, what I showed you. So the proof was so slick and so quick and elegant and you know, short. And by the way, they did it, you know, for arbitrary, not necessarily II1. They did it for types 3, type any, you know, amenable action. That Ornstein-Weiss basically never wrote their entire paper. So the whole thing remained as an announcement, in which, however, they indicate that they sketch the proof, and they, in particular, they do this kind of what they call tilings of the amenable of an amenable group, which is pretty important, you know, way of covering the amenable group with Fellner sets, and that is something very structural result that's very important and has been very useful, in particular in C-star algebra theory recently, you know, in C-star dynamics, so to say. And okay, so that is the, you know, thing that Ognanu used a lot. Okay, so that is so what he proved it first for Z square, by the way, but where these stylings are obvious, because you know, that means amounts to covering the plane with squares. But in general, you know, you needed something similar with that, and he needed with his argument. So I have the other proofs of this result. One which I can, it's very convincing, I think. So here is, so what you, in all these things, you want to prove that given an action, an arbitrary action, or rather a cocycle action of an amenable group, you prove that you sort of built up in it, okay, in your hyperfinite II1 modulo perturbation. You are allowed to do perturbation by unitaries, and you built in R like a model, a way you reconstruct R in a manner, for instance, say by miracle, perhaps you can even construct inside copies of 2x2 matrices that mutually commute, and with the group acting on those matrices by Bernoulli shift. That's called a model. So you built, you fixed yourself some model that you think you can recover inside R, prove that your action is basically that model action, okay? That's also the strategy that Einstein used when he proved his famous theorem about two automorphies having the same, two Bernoulli automorphies having the same entropy, you know, being a conjugate. And for instance, in the case of Z, you may want to do like this. On R, so what you do is the basic tool is here the Rocklin theorem. So you let's say that you look into R cross Z, right? And so I'm trying to use the notations and the intuition we developed for the for the Kohn-Feldman Weiss, for instance. So given any set of elements, the thing is that I can you can prove that given any set finite in R, so this is, by the way, it's given by you know, things like this, right? So I wanted to emphasize the canonical unitaries. Okay, so for any finite, any epsilon, and let's fix also a natural any n, or rather let's call it k. Okay, I want to prove that there exists a projection Q, sort of infinitesimal in R. So that's the way you have to think, like we always do. So small projection that avoids F, it's always relative to the size of Q, and which satisfies that, let's call it sigma. Okay, such that sigma g, so this UG, but let's use sigma g. Sigma g of, yes, you will understand why I use this k. Sigma, sorry. Actually, this is z, so this is just one automorphism. So let's call it theta this time. So theta to the n of q are mutually orthogonal. Again, this is approximate. Okay, theta to the n for n from 0 to k. So in other words, you want to do something like this with your automorphism, okay? For all this is arbitrary, so k can be huge, okay? So if this k can be huge, and you can do that, then you can then return with an add of with a partial isometry, so you can perturb your theta with the partial isometry that moves you back, and which, you know, what will it add with respect to the identity? It's like perturbing theta with an add u, okay, such that this u is basically, you know, almost like, I mean, of course it's not one, but the effect is completely controlled by just the size of this incremental thing, right? Incremental thing, with respect to the overall size, so it's of the order, this is over order of 1 over k, or delta times delta of tau of q. Okay, so I'm keeping this, but also that. So, altogether, what you can do with this, and I hope I can, be quite convincing after all we've done, is that, each time I'm giving something like this, I'm doing this infinitesimally. This is not hard, okay? What I've just set up to here is really not hard, okay? Because of the hyperfinite, the definition of hyperfiniteness and so on. So what you do though from here is a maximality argument, and you fill up the identity. So for that, it's really kind of useful that you have these neat Fellner sets, for Z. I'm using this, this long sequence 1 up to K, and we're taking K huge, okay? So you see, I want this 1 over K, very small. So I fill up the identity, and so I can, with the maximality argument, can then, I'm claiming that there exists, perhaps we should have called this U0. There exists an actual, a unitary that now, really does this. I mean, this now. These are really mutually orthogonal. Maybe I should say n from 0 up to k minus 1. Okay, so the powers now of this new automorphism, this will be mutually orthogonal and filling up the identity. So the sum equals 1. So, okay, I think this is okay. And what did I do by doing that? It means that I created a situation where, I have an K by K matrix algebra on which, with a little bit of care, this implies that this new automorphism leaves a K by K matrix algebra invariant, and on which it acts like the permutation of, the cyclic permutation of 1, 2, 3 up to K. I mean, add of U where, I'm sorry. So it's like, it acts like add of this unitary. Okay. So now, and then you have the rest. So you split off, you take this matrix algebra, relative commutant in R. And now you continue, okay? So the thing is playing with this K. So this is my defect for this, okay? But I'll do this with an extremely rapidly increasing K, okay? And I split this way R as a tensor product okay, this way with, now theta, I perturb it with unitaries, with an infinite tensor product of unitaries. But their product will be a unitary in R, because they are 1 over K closed, so 1 over Kn closed, and I can make that convergent. So it will be another, let's call it add capital U, okay? Such that, okay, and which will act on this guy as the following model. My model is the following, is the tensor product of add of little un, where these are the cyclic. It's the, okay? This is an action of, okay? This is Cohn's theorem for Z. Now, clearly, you can make this work for Z squared, because it's nothing, it's just, now I claim that you can do it, and by the way, it gives you an action, a true action, okay? So you perturb it and you show that it's isomorphic to this action. there are several problems here. You may not, I mean, in the case of Z, you have no cocycle. At Z squared, you have a cocycle. So how do you deal with that? Well, you see, there is this thing that all this you can do in the commutant, okay, of stuff. And that's what you do if you have a cocycle. You avoid the cocycle. You only, right, so it becomes a little bit technical, but you know, it's not such a big deal. In the case of Z square, already you have to deal with that, okay, because you may have a cocycle, okay. Well, what do you do for arbitrary gamma with this strategy? So the way you can do it exactly the same way is you prove, rather than proving that, you know, to untwist it and all that, you know, the way, for instance, Ognano did, you prove that your action is cocycle. So you construct a model cocycle action, okay, which is somewhat unusual. And your cocycle action is this. You construct huge Fellner sets, I mean more and more invariant sets, Kn, and your model will be this. So it's in Kn by Kn, I mean cardinality here, but matrix algebra, okay? So these are almost invariant to, say your group is finitely generated, okay, gamma. So these are more and more invariant to your generators. And then I do exactly the same thing. So this is this matrix algebra. So the Fellner set, they are more and more invariant to gamma. So gamma will displace a bit this matrix algebra, and I bring it back. So, and every time it's like having a permutation of your Kn, that a finite permutation which imitates gamma, right? But which I fix once for all. So you see, they are really indexed, my matrices, by Kn as a set. And so Kn is displaced, so this is a set, the set Kn is displaced by the elements in the group, I mean the generators of the group, and so I have to decide where these things go. And I put them once for all to go, and I make some prescribed, you know, choice, but which will be it for, you know, that will be my model. So, so I have some chosen permutation, in other words, of the sets Kn, okay, which imitate my group. I do that, okay, and I take this again, the infinite tensor product, and with the same technique, you build this model cocycle action, because it will no longer, you have some perturbations here. But if you do this with huge, you know, this is extremely invariant. You know, it means that what goes out, which every time what goes out, you will have to use a perturbation by a unitary to put it back. And that unitary will be close to 1 with this kind of, you know, level of accuracy. Right? With this level of accuracy. So if this, I can make it extremely fast, you know, going to 0, then the product of those unitaries will be a unitary. But it's a perturbation, so it will add, even if you started with an action, it becomes a cocycle action this way. But it's your model. This is your model. Okay? There is another proof that you can give through subfactor theory, but let's not get to that, at least not for now. Okay. So, yeah, I wanted to at least, you know, wave my hands and try to be in a convincing manner, you know. Anyway, the proof I told you is actually, you can find it in a paper of mine in Yasu's journal. What's the name of that? International Math Journal, I think. Okay. The second approach is through subfactor theory. I'll explain that because it's not here at the moment, so let's move on. Okay, so now we have the case abelian, right, and the case factorial. So in general, when you have a regular subalgebra in a II1 factor with this condition, and say I denote by L infinity of x the center, you know, I write it as a functional, as the L infinity of some probability measure space with the mu given by the restriction of the trace on M that you restrict here. Of course, the assumptions imply that B is homogeneous. And that says what? That either B's will be of this form, so it is of type 1n, okay, right? Or it will be like this. It will be an integral, okay, of II1 factors. Okay, that's why, you know, pretty, I mean, it's, I think it requires, you know, this, what do you call this, well, you can write it as a measurable field of II1 factors, like an integral of II1 factors. You know, this is all for Neumann, Mare for Neumann. Actually, it's just for Neumann who, you know, did this first. So now, if in addition M is the hyperfinite II1, you can, you know, say it better, because at each point this B sub t will be isomorphic to R, and you can make these choices in a sort of nice measurable way. So you end up, you know, proving quite easily that this B sub t are, I mean that B is a tensor product, really, like here, okay? R tensor L infinity of x. So the normalizer will define, well, first of all, it will act, the normalizer, ergodically on the center. It has to act ergodically because otherwise M will not be a factor. But it may act, so you see what happens, even in general, not necessarily here, but here is very obvious in this case. But, okay, namely that you have a groupoid, you have an acting groupoid rather than like in the irreducible case where you had an acting group, a normalizing group. Here you have a normalizing groupoid. So these are the points, say Ts, you know, of this is your space X. So transversally is X, it acts on this space X, okay, as a countable equivalence relation, okay, and so you have your, you know, your equivalence relation, which you can view as arrows, like, you know, as a groupoid already there, but that's a very easy groupoid. However, in addition, here you have at each point a II1 factor, and there you have, you know, you may have isotropy. So you may, at each point you may have a group, right, sort of acting. And you think it's very intuitively very obvious, okay? Especially, say, you know, I mean, actually it's not good to, the intuition is not good if you take X to be discrete. I mean to be, you know, just finitely many points, because then, you know, it trivialized, the situation becomes trivial. So, okay. So it's a discrete measured groupoid, okay? Let's call it, so there is an object, what I'm trying to say behind, like we had before, we had a group in the irreducible case and an equivalence relation in the case, abelian case. And here I'm saying it's a combination of the two. You have the equivalence relation transversally on x0, which, by the way, this is the space of units of the groupoid, and above each point in the groupoid you have an isotropy group. Okay, it's just a genuine group, genuine groupoid. Okay, above each point unit you have a group in a groupoid. Those that have the source and the target the same point. Okay, so it's G tilde, but I mean I'm just not writing every time that it's the one that associated with B into M. Actually we have that with the cocycle of this groupoid, so there is an abstract object with an action of G on B, okay, alpha B. A cocycle action, I'm sorry. And again, so there is, obviously, conceptually this is a bit more complicated, but it's not a big deal. I'm trying to kind of, convince you about that. So the iso class of B into M is completely encoded in the cocycle conjugacy class of this groupoid action, okay? Okay, so it's the groupoid, but also the cocycle action. Huh? So that's why it's a bit complicated. So in the factorial case, though, I mean, the nice thing there was that G becomes a group. You have just, the X is just a single point, and you just have a group. Okay, this is your gamma at that point. You still have the, by the way, this is general. No, I'm not even, you don't need, except that I should have not used the integral thing. Actually, no, this is good. It's a field, a measurable field of, okay. So, in the case R, n equals R, the discrete groupoid accounts for an amenable ergodic countable equivalency relation along the space of units. This is very trivial that, it's the equivalence relation is amenable, and also the isotropic groups at each point, they are also amenable. And acting outerly on also B at T, of course this is just this, so, okay. Okay. So now let's get back with this kind of groupoid image in mind, notation. What happens in the case B abelian, G is just the countable relation. You have no isotropy, so it's just arrows that displace the points, okay, the equivalence relation. What happens with alpha? There is no alpha, okay, in that case, okay, it's sort of intrinsic. It's just the equivalence relation, because I mean, R itself is also alpha, okay? For along this line, okay, alpha is just, the equivalence relation. So giving the groupoid gives you also, okay, the alpha. So, by the way, I want to point out that therefore, what Kohn-Feldman-Weiss theorem says is that there is just one amenable countable equivalence relation, just one amenable countable groupoid. I mean, groupoid with, trivial isotropy. And it has vanishing cohomology, also, these two things. There is just one, so that's how you can reformulate Kohn-Feldman-Weiss. You see that it's much stronger than Ornstein-Weiss, because it says that there exists, I mean, it's a beautiful theorem. It's just, the Kohn-Feldman-Weiss says there is just one countable equivalency relation. It's like saying you have just one amenable group. But, I mean, from the orbit equivalence sense, a point of view, that's it indeed true. So it also implies the Kohn-Feldman-Weiss that for each n there is just one regular inclusion of type with B of type 1n. So if you take matrices over n by n matrices over an abelian, okay, if that's your B, obviously this also says the uniqueness. So for each n you have just one regular subalgebra. Okay, if B is a factor, the Gouverneur, this is just, you know, reminding you that that was. So what is it left? We have, I know, however, I wanted to point out that Ogneanu trivially implies the case when Z of B, the center of B is atomic. Atomic means it's just finitely many, because, you know, they have the same trace, the atoms, because of the ergodicity of the action, so they have to have the same trace. That's also, you know, there exists a unique for each cardinality of, you know, of the center, of the dimension of the center. So there is, the case left is therefore when the center is diffuse, okay, non-atomic, so in other words, B is of this form, okay? So in other words, we are left with the problem of classifying cocycle actions of groupoids, okay, onto this space, up to cocycle conjugacy. So now, when V is trivial, so when there is no cohomology, okay, this was solved by the Sutherland Takesaki in 1985 by their theorem. So they proved that any two actions, alpha 1 and alpha 2 of the same amenable groupoid G on this algebra are cocycle conjugate, equivalent in any two regular inclusions like that with trivial cohomology, so with no twist, okay, are conjugate by an automorphism of R, okay? So now, by this result, it follows that we are left with proving that any two cocycle for the cocycle action of a groupoid on this thing, of an amenable, discrete amenable groupoid. Why do you call it discrete? The discrete refers to the, it's like saying, the reason you say countable equivalence relation, or, you know, so it's discreteness in a sense, you know, this way. I mean, and at each point you have a discrete group also, a discrete countable group. So all discrete is, you know, to remind you of all this. And so you are left to proving the, you know, this vanishing cohomology thing. Well, this is not easy actually. You know, it's a very subtle problem, and this is the last thing we have to prove, and that's what we will do. I guess maybe it's the proper moment to take a break until 05. So this is, yeah, I'll explain. We will take it from here after the break. Let's start then. As I said, this the vanishing cohomology of the two cohomology is a hard problem, and it's extremely interesting. I view this as a really, you know, very nice and also very beautiful problem. I'll kind of develop it beyond what we strictly need. So I'll go into more general considerations. So first of all, I wanted to so remember, in the hyperfinite II1 case, we know to untwist two cocycles for cocycle actions of amenable groups on the hyperfinite II1. That comes from Ogneanu's theorem, okay? we want to do this same thing for fields of II1 factor, measurable fields with groupoid actions, with groupoid co-cycle actions. So it's really a significantly more complicated problem, really significantly more complicated. And after all, why not look at that, you know, for completely arbitrary fields of II1 factors with co-cycle actions of arbitrary amenable groupoids on it, or perhaps not even amenable. After all, we saw that F2 untwists, so always there is no co-cycle there. Well, let's first talk some more about this problem in the II1 factor case, but where we no longer look at the actions, co-cycle actions on the hyperfinite II1, but on arbitrary II1s. Okay, so what happens, there are two places where we can try to go beyond amenability. On the group side, okay, we saw that is also interesting because, you know, F2 has no cohomology. Or on the side of the II1 factor, okay? So as it happens, it's true indeed that any countable amenable group, any free co-cycle gamma action on any II1 factor untwists, okay? So this is a result, well, I mean, so I have written this paper early in 2018. I considered it done a long time ago, and I you know, kept saying that, you know, this is sort of implicit in my papers. Why is that so? It's because, so I have done it for Z square, for this case, in 1989, and that was an important, you know, moment because it triggered lots of, it was in a contrandu node, so I did only sketches of proofs, but it was an important, you know, an article in the contrandu. I think, you know, with sufficient indications for the proofs, it brought in the idea of taking the Poisson boundary for the graph of a subfactor in John's theory of subfactors, which developed into lots and lots of things. Anyway, so it was an important, you know, very important at that moment. So then things developed in subfactors. So I was using subfactor theory, you know, to prove this result. As you will see, the technique for proving this result is still subfactor theory, pure subfactor theory. And really, I think it's even, you know, nowadays, perhaps, you know, the most striking and unusual application of subfactor theory completely outside of subfactor theory. Okay, so this vanishing of the cohomology. And I'll explain largely, you know, why subfactor theory, you know, was necessary, right? Well, so things evolved, and what I needed, in fact, was gamma with polynomial growth, and more generally, gamma having a set of generators finitely generated in any case, for sure, and polynomial growth, or more generally to have a set of finite generators for which the Poisson boundary is trivial. So there are no harmonic functions with respect to that. Then things developed in subfactor theory, and there is a remark where I explain in a paper of mine from '97, symmetric enveloping algebra, where I explain in details how you do obtain, for instance, classification of amenable subfactors with arbitrary amenable graph. So in a way, that also, you know, indicates how to do this. However, because I needed this result in some other things, I was thinking, you know, to sketch again the proof, and I looked back at all this history, and I realized that, you know, my God, at that time, it's true that those indications were sufficient, but, you know, that has been sort of lost. I mean, the younger people obviously will, you know, I mean, what am I saying, younger people? I discussed with, you know, my collaborator, you know, and friend Stefan Vaz, who told me I don't understand anything of what you did there. So I realized that, my God, I mean, you know, I better write this thing down, because it's, you know, you see, things evolved, and there are other people, and those people, I mean, you know, they are not the same of those who were at our conferences in subfactor theory at that time, where I could just say, well, it's obvious, you know, you just do like that and it's clear. So, which is basically what I said in my contrandu note, and everybody was happy and, you know, was accepted by the community as an actual proof. I looked back at that again and I thought, well, this is nothing, you know, it just doesn't say that much. Anyway, so I wrote completely the proof of this result, and it's not trivial, in fact, you know, it's not that short, in fact, when you give all the details. And of course, this immediately gives you this more general result, that you have that any action of a group like that, any cocycle action of a group like that, a free product of amenable groups, even with amalgamation of finite groups. So you see, I gave the title of my talk is the ubiquitous hyperfinite one factor, and I was saying in the presentation that, you know, lots of what I will be doing depends on certain remarkable embeddings of the hyperfinite one factor in other factors. Well, this is a perfect example, but there were before, however, they were implicit, something I will emphasize hopefully tomorrow. Okay? So this whole strategy for proving this vanishing is the following. I mean, the idea is simple, and actually this is an idea I had very early, you know, like in 81, 82, except that I could not do it. So the idea I had was to build embeddings of the hyperfinite one that are gamma invariant, equivariant, I'm sorry, okay? Modulus aminar perturb. So you perturb each alpha of G, okay? You perturb each alpha of G by some unitary, if you want, but with that, you know, sacrifice, you getting into, you know, having modifying it to another cocycle action, but which really leaves an invariant. Now, why you want to do that? Because then you want to use Ognano's theorem and say I'm untwisting it on R, and then claim I've untwisted it overall. However, if you think a little bit, it's not that, you know, obvious that that solves the problem unless this subfactor R is kind of big in N. What you want is really this condition. So not only big in N, but big in N, you know, relative to this action in some sense. So it's this trivial relative commutant in the cross product that you want, okay? Why? Because you see, just having some things that normalize this new alpha prime G doesn't mean necessarily that you have the same group acting. You see, you may have introduced some, there may be some unitaries So some that are in N and normalize R, and which can give you a much bigger group, perhaps not even amenable, that's above this whole thing. Do you see what I mean? It's a co-cycle action. So, you know, every time you do this, okay, it gives you this add of something. Now, okay, and this guy can act outerly on your hyperfinite one factor. Okay? So, but that with that condition it won't. It will just keep, so in particular this will imply that your new cocycle V prime sits in R. So when you are untwisted in R by nano, you've untwisted it all. Okay? So that's the idea. Okay? So now, how you prove the existence of such an R, so an embedding, okay, so it comes to this, so it's this theorem, okay, let's put it here, okay, so unlike the vanishing of the cohomology, which we saw is not specific to amenable groups, okay, even Fn satisfies it, okay, this property of being able to build a hyperfinite, a big, large hyperfinite that's normalized by your group, modulo some perturbations, it's really actually with if and only if the group is amenable. I mean, the universal property. So by this I mean this theorem actually is true. Any any cocycle action, let's change the notation because I want to separate it from the previous page for the action. Any cocycle action sigma of a countable amenable group gamma, I should have added 3. On an arbitrary II1 factor admits an inner perturbation that normalizes a hyperfinite subfactor with this property if and only if gamma is amenable. More precisely, if gamma is non-amenable, I mean, you have one implication. This, you know, if you have this, you have such a subfactor indeed. And if gamma is non-amenable, then there exists some action, more specifically, there is a free true action of gamma on the free group with infinitely many generators such that no inner perturbation of sigma can normalize a diffuse, even abelian, a diffuse, I'm sorry, amenable subalgebra of N. Now, the proof of one, as I said, uses subfactor techniques, and you construct R. You see, this is the strategy. You construct this subfactor equation. Sorry. So you have gamma. We use now this notation, right? And say gamma is finitely generated to start with, and then say by G1, GT, okay. And then you construct, you take this inclusion, let's call it M sigma. I should put also the generators, anyway. Where this factor M is it's N plus 1, this is N. Matrices over N, and this is actually this inclusion where you put X from here into this. Diagonally, and 0. So this is a subfactor situation with finite index N plus 1 square. And if the graph, what's called the standard or the principal graph of this subfactor is the Cayley graph of the group corresponding to this finite set of generators. And so there is this tower of algebras and tunnel of algebras, which are specific to the theory of subfactor. And the R that we want to build in N, and that's invariant to this, is actually constructed through, you know, as an appropriate choice of a tunnel of subfactors. So it's like a sequence of subfactors with finite index, whose relative commutants are finite dimensional algebras, and R is obtained through an appropriate choice of this tunnel, so that when you take these relative commutants, well, first of all, it will give you a factor because, you know, the amenability plus actually also, you know, there is a more, in the case of trivial Poisson boundary like this one, it gives you automatically a subfactor. That's what means to have trivial Poisson boundary. That this is factorial, this limiting thing. And just by the fact that this kind of relative commutants, it's, how to say it, it's in your face that you can interpret that as a you know, as a subfactor of N that's left invariant by the action. It's really quite you know, amazing how, you know, just by using the subfactor intuition, you know, just it's just you know, all the point is to do this construction. But after that, you know, the fact that this is what provides you. So if you do this construction, so that, by the way, I forgot to say, you want to do it in a way that the relative commutants, so well, they automatically say, you know, generate a factor, but you want that to be kind of big in the sense of, you know, the model inclusion that you obtain as a relative, you know, from the relative commutants has exactly the same relative commutants as the initial thing. That is, you know, just translating this property here, okay? And that's, you know, through a certain technique of random choices, random embeddings of the hyperfinite II1, which is something I'm leaving for the last lecture, okay? This kind of embedding, techniques for embedding hyperfinite II1. But it's modulo that, you know, it's really taking you by the hand through subfactor techniques, through this subfactor intuition. Okay, the other thing, yeah, so basically for this second part, if you take here the Bernoulli gamma action on the generators, then, you know, what I did with Taka, proving that, you know, you have no diffuse amenable subalgebra of the hyperfinite factors. Well, any amenable has the normalizer must be amenable. So that's what you use for the converse. So indeed, this is a property that's specific to amenability. Okay, so now with this in hand, this is what we could prove for this kind of fields, of measurable fields. This is a newer paper at the end of the summer last year. Was really a follow-up of discussions we had, Dimash Liartenko, Stefan Vas, and myself at IPAM during the program last spring at IPAM. So we proved that if G is a discrete measured groupoid with units, say, X, and you take a measurable field of II1 factors over this X, and you assume that G is amenable, and that you have, and then you take a free cocycle action of this groupoid on this measurable field of II1 factors. Then the cocycle V is co-boundary. So I write it, kind of roughly. It's obviously, this is a more complicated object, the groupoid fields of II1 factors, etc. So it's clear that, we kind of use we leave it like that. I'm not even giving, even it would have taken me a lot of time just to explain very carefully and rigorously what a group, such a discrete measure groupoid is. And I avoided that, okay? So, well, with this in hand, of course, it means that we proved our classification of regular subalgebras, right? So let's point that out. So with this, we do have the two regular for Neumann subalgebras in particular, satisfying this R conjugate by an automorphism of R if and only if they are of the same type and they have isomorphic associated discrete measured groupoids. So this is what was missing after Sutherland-Takesaki, okay? This vanishing cohomology. Remember, this was the missing piece. So we have that, therefore we have all this classification. It's okay. Now there is a second part to our theorem which is not evident, okay, I would say. So we were also able to prove that any such regular subalgebra of R contains a Cartan subalgebra, and that if you take two copies of Cartan in B, okay, then there exists an automorphism of R that leaves B invariant and takes A1 onto A2, which is kind of, I would say, well, for sure it was not known, but also, I mean, we were kind of pleased and surprised to get also this as a, like a gift, like a bonus. Okay, so about the proof. The proof uses the vanishing of the two cohomology for cocycle actions of amenable groups on II1 factors, so the thing I stated before. Of course, you kind of use, there is nothing you can do. You also need to know that, in this direction things vanish. So Kohn-Feldman-Weiss enters in this also, okay? No, but this part refers to this. So, I mean, it's like I'm applying, so which we apply to the isotropy, of course not Kohn-Feldman-Weiss, but this. It's a bit misleading how I formulate it, which we apply to the isotropy groups of the amenable groupoid G. I mean, we apply the whole thing to extend to the entire G. The thing is, I mean, of course, you see, I mean, intuitively, what do? You vanish it this way, and you vanish it at each point, okay? You cancel it. But of course, this is a measurable choice. You have a big problem there, okay? So it's not like you cancel the cohomology at each point, and that's that, right? Along this line, it's fine, because, of course, with Kohn-Feldman-Weiss, you do it measurably. But with doing it at each point, certainly, it's not working. So to extend indeed to the entire G, we have to make equivariant choices of the two cocycle vanishing for the isotropy groups. Okay, where the equivariance, of course, will have to be with respect to the isomorphism, from gamma T to gamma S given by the conjugation with an element in G with these arrows, right? And this you have to do, okay, in a sort of measurable way. Okay, so obviously, at least I convinced you that there is a problem there and that it's probably not simple to resolve. So actually the proof of this thing depends on two key points, okay? The first one is a technical result showing that such an equivariant choice does exist, provided that the two co-cycle vanishing for each group, okay, can be done in an approximately unique way. Well, by the way, if you could do, if the vanishing of the two cohomology is unique, okay, somehow, you know, by a miracle, like, you know, as I will show you later, for instance, if the groups are finite, then it is unique in some sense, okay? Okay, well, it's actually, luckily, it's sufficient to do it approximately unique, okay? The fact that the two co-cycle untwist in an approximately unique way amounts to, let's translate that into some sort of, you know, this is kind of, I purposely did it, you know, in a vague manner, but this is what it really means, okay? Untwisting in an approximately unique way really amounts to the fact that, so choosing various untwisting of your various two co-cycles, you know, so untwisting a two co-cycle, you remember, it's a derivative of a one co-cycle. And saying that you have a unique such solution is like saying that you have that any one co-cycle, any two of those will differ by a one co-cycle. You see that right away, okay? That's general, you know, cohomology theory. And so if you can prove that that one co-cycle vanishes, I mean, it's a co-boundary, then you prove your uniqueness. Well, actually, you have to do that approximately, so that amounts to the fact that any one co-cycle is approximately co-boundary. Now that we came to a problem which is clearly formulated and which we will discuss. Okay? And that's the second point. The second point is to prove the such approximate vanishing one. So first point is to reduce it to that, and second point, key point, is to prove that any approximate vanishing one co-cycle for an arbitrary action of an amenable group, you know, is, I mean, any one co-cycle is approximately vanishing. Okay? So that, now that's for gamma t, and for n sub t. So it's a co-cycle on a II1 factor. This is down to earth, you know, no longer all these, you know, terrible complications with groupoids and with fields of arches. It's a clear problem. So this is the problem. Approximate vanishing one cohomology question, okay? First of all, what's the definition? One co-cycle, first of all, for an action is a map W from gamma to the unitaries of n. This is a II1 factor, n here, such that you have this, okay? The co-cycle W is co-boundary if there exists a unitary in n such that Wg is this form. You can see immediately that this checks. And this is, you know, so it comes from a zero. It's the derivative of, you know, so previous, I mean, will be like the zero, I mean, just taking one element. It is approximate co-boundary if there exists a sequence of unitaries such that Wg is approximately so. Okay, pretty self-explanatory actually what approximate vanishing should be. That, by the way, please notice that it's absolutely the same as saying that W is co-boundary as a one co-cycle for the ultra power of the action on the ultra power of n. Now, that's a moment where we should say what the ultra power, ultra product are. Let's see, yeah. So it's something we did not really define. when I gave the list of operations, constructions of factors. So if Mn is a sequence of finite factors, so they can be II1 factors or n some k by k matrices, each one of them. And I also want, because I want to get some interesting things, I will take, say these are matrix algebras, the dimensions could go to infinity. So I don't want to take constantly just 2 by 2 matrices, okay? And I take also omega of ultra filter on n, that's non-trivial. So that means it's like thinking omega is in here, right? It's a point in the stone-check compartification, and which is not on the, the n part. It's really a point at infinity. Okay? How do you call this? Non-principal, no? Free ultra filter or non-principal. Okay, and then I take the algebra L infinity, not L infinity, the direct sum of n by n matrices. Okay, so let's call this M. And on this I'm taking. So by the way, if all Mn are equal to n for all n, this is the same. This becomes little L infinity of the bounded sequences with values in n. Okay? So these are bounded sequences, but with the entries being in Mn. Xn is in M. Okay? And on this I take this trace, this functional, tau omega of a sequence. Remember, this is bounded in uniform norm. It's this. So I take the trace on Mn. Here it's kind of convenient to use the notation of the algebra. Okay, and I'm taking a Banach limit, a limit over omega of this. Okay, so this is by definition this. That's the tau omega. What is the meaning of that? This is a sequence that's bounded, okay? Say in this case, it's like it's in L infinity of n. It's a bounded sequence of scalars, and you apply omega to it, okay? So you evaluate it at omega. It's a function in this, in little L infinity of this, and this is, you know how this space, this, okay, it's the one that gives you L infinity of n to be the continuous on omega, right? And it's, okay, so it's a trace on M, and what you do is you take your ultra power over omega, along omega, ultra product, I'm sorry, omega ultra product of Mn is this M, the quotient by the ideal of this trace. The ideal of the trace given any trace on a C-star algebra, this is a C-star algebra, M is a C-star algebra, and you have a trace. So this is the set of all, let's call them X. Okay, by polarization, you see that this is a vector space, and it's actually an ideal, two-sided ideal in M, and it's star, it's everything, it's closed, so this in C-star theory, C-star algebra theory, this will be a C-star algebra. And moreover, it obviously has a trace. Tau omega implements a trace, which after you have done all this, it's faithful. Faithful. Trace state. That's faithful. And here is one of the nicest, applications of that characterization of abstract characterization of a II1 factor that we gave. The point is that the unit ball, so the unit ball of this guy, okay, is complete in the norm 2, in this norm 2 given by this on the quotient. So it's a II1 factor. So, well, it's a finite for Neumann algebra, but you see immediately this is a factor. I mean, the center is trivial, and this, so it's this, obviously, because of this condition, the dimensions of Mn tending to infinity will easily show you that it is diffuse, so it's a II1 factor. It's an enormous II1 factor. It's not separable. But it's very useful for analysis, arguments and formalism for Neumann algebra in II1 factor theory. It's very important because of that. So not to study by itself, although logicians may differ in opinion on that. In any case, it's more, we use it as a tool in II1 factor theory. So you see clearly, for instance here, you see how beautifully, obviously when you have an action, so if all of them are the same, you call this n omega to the power omega, okay? So this is n omega if all, if mn equals n for all n, okay? So obviously, applying point by point, entry by entry gives you an action sigma omega on n omega when you have an action. And if it's a cocycle, it's a cocycle action. There, one cocycle, etc. Okay? So this is what we were able to prove. So if gamma is amenable, then indeed, for any free action of an amenable group of the group gamma on a II1 factor, or rather, so let's just take 1 and 4. So if gamma is amenable, then indeed any one cocycle W for any gamma action on a II1 factor is approximately coboundary, or if you prefer, it's really a true coboundary as an action on n omega, so as a cocycle for sigma omega. Actually, it's an if and only if. It's a characterization of amenability, so you also have, it's an if and only if thing. And the key point here for this equivalence is this point 2. That in fact, these are also equivalent to the fact that for any free action of gamma, the fixed point algebra of sigma omega on n omega is a subfactor with trivial relative commutant in n omega. Okay? And I would say it's unexpected. I mean, well, anyway, so let me show you before the end of today's class the proof of this, because that's nice. And anyway, we kind of missed to do too many proofs except for this sketch of proof for Ocleano, etc. But otherwise, we didn't do today too much proof. So let's do a proof. Actually, I think, unfortunately, the first part is in details here. The second part I'll have to do it at the blackboard because I didn't have time to put it on the page. Okay, although I just needed to paste it from a place, but I was afraid to do some to corrupt again the file like it happened to me yesterday. It was too rushed and I didn't want to do it in the last moment, not to have problems with the processing the file. So the proof of the approximate one cohomology. So let me go back to what I told you about this result of Jones from his 1980 paper, his thesis. I told you that he showed that not only any two action of a finite group on the hyperfinite one are conjugate. I mean, that by itself already shows that in that case you have the vanishing of any one cocycle for the action, for the gamma action. But that part actually is true for any action on any of the finite group on any II1 factor. So he proved, in other words, that if, any one cocycle for a free action, sigma of a finite group gamma on an arbitrary II1 factor is cobound. So his proof actually only uses the fixed point algebra of any such action is an irreducible subfactor. Okay, that's what you use. So let me show you the proof. So let sigma twill, so I'm taking a cocycle W, I forgot to take it. So let's W be a one cocycle. Sigma is my action. Sigma is my action. Yes, here it is. And W is my one cocycle. I take it normalized. W1, W of E is equal to 1. Okay, so I construct this action, sigma tilde, to be simply on 2 by 2 matrices. So this is, by the way, make a parenthesis, this is pretty famous. And this is the so-called Korn's 2 by 2 matrix trick. Okay, that's how he untwisted cocycle in a, it's a pretty, famous trick. Very nice, very sleek trick. So I'm taking sigma tilde to be the, just this is the plane amplification of sigma by 2 by 2 matrices. Okay, so you amplify by 2 by 2 matrices. Right? You just apply sigma g to the entries. Okay, so so I'm taking the matrix units that come with these 2 by 2 matrices, Eij, and I'm now taking this cocycle, this function Wg twiddle, which is E11 plus Wg. So here I take 1 and here Wg, direct sum of the trivial cocycle, one cocycle, and the cocycle Wg. Okay? Okay, I claim that this is a one cocycle for sigma tilde, and I let you check that, it's a triviality. Okay, okay, so this is, then I can construct this sigma g prime, which is the perturbation of sigma tilde with this one cocycle. This will be an action, because this is a one cocycle. Okay, so this is a true action. Okay, so its fixed point algebra is trivial subfactor with trivial relative commutant. Well, that's a general fact which was kind of well known, but certainly emphasized by Jones. So Jones emphasized quite a bit the fact, but Sutherland, I don't remember who in fact really did this, probably simultaneously, independently. Sutherland, Jones made lots of observations. This is really trivial. Any free action of any finite group on any II1 factor, the fixed point algebra is a II1 factor which is irreducible. Okay? Or the fact that you have, so the existence of a unitary element in N that satisfies this, it's trivially equivalent, and that is another exercise, to saying that these two projections, E11 and E22, which of course are in the fixed point, right? This leaves, this, and also sigma, the initial sigma leaves E11 and E22 fixed. So altogether, this sigma prime will leave these guys fixed. they are in Q, which is a II1 factor. These have trace equal to 1/2 each one of them, so they are conjugate. And by what I'm claiming, it has to be, that is the same as giving you, this simplistic. This is nice. I mean, so this is constraint, okay? And, okay, so the above shows that if we can show that this was written in the last moment. So the above shows that this. So this, what we just showed was that if we can show this thing, where is it? This. So if we can show that any free action, its ultra power has a fixed point, a subfactor with trivial relative. If we can show this, then we have 4. So 2 implies 4. It's the proof. I mean, I gave you the proof. Whenever, because, of course, that's because the omegaification, okay, of sigma is, behaves well with respect to the omega. So it's this that we have to, it's this sigma triple prime that we take, But this is also an action, and it's also an ultra power. So if we offer an amenable group, so if that is true for any of that, it will be true for this, and therefore, you have that 2 implies 4, right? That's what I was saying here, but so the above shows that 2 implies 4. Let us show that 1 implies 2. So that means this 1, if gamma is amenable, then the fixed point are. So I mean, this is the crux of the matter. After all, we are interested in 2 implies 4. Forget about the other implication. We want to prove that gamma implies this, right? This is our, because this is what solves the problem with the vanishing of the 2 cohomology, you remember. So, it's fun to have these equivalences, but it's 1 implies 4 that we need. So we already have 2 implies 4, let's prove 1 implies 2. So this also, it uses quite a bit, this kind of random embeddings of the hyperfinite II1, but in a hidden way, okay? So this is what you do. So if you have this action of a countable group on a II1 factor, so this is like a black box here that we will be using like we used the local quantization lemma, and it's in that family of results, okay? As I say, it actually uses, random kind of embeddings of the hyperfinite one in II1 factors. So with that, you can prove this thing, that you will always have in an omega unitaries with the property that, after you can put this thing, you can switch and actually any kind of separable subalgebra in N in a way that so that sigma g omega operates on this as the free shift. So this you can make them freely independent, are mutually free independent, okay? Meaning that the traces of any, so it's like having that these algebras generate the free products, they generate like this. And, okay, so a copy of that with, by the way, I made my choices, okay? This is not quite N, it's something isomorphic to N, it's U and U star. By the way we made our choices, sigma g acts on it by shifting the coordinates, right? So it means that basically I have a very concrete, out of a completely arbitrary gamma action in n omega, I have some piece on which sigma acts in a very concrete manner. Okay? So the thing is that on this free Bernoulli action, you can very easily construct things that are approximately fixed by sigma omega, by the action. How? This is very easy. You just take you take Fellner sets and you sum up. Okay, so you take, say, a B. Actually, this is U and U star, right? But okay, so you take here a semicircular. You can take any kind of element, but let's take it semicircular, and then you take sigma G omega of B, and you sum this up over a Fellner set. And you divide by this, by the size of the Fellner set, well, actually to 1 over 2. So this way, you see, these are, in any case, with respect to the L2 norm, they are mutually orthogonal. So this gives you an element that has norm 2 equal to 1. But the thing is that because of the entries being freely independent, any kind of things that you take a little L infinity of, things that are freely independent, in little L2, I'm sorry, of things that are freely independent, the norm 2 is essentially the norm infinity. This is one of the, Voiculescu's absolutely initial observations in free probability. And so this actually is a substantial, operator. It's not like it has a bad shape. Actually, it has a semicircular shape itself. It's a beautiful semicircular system of norm 1, okay? And obviously, because of my construction, is almost independent to sigma G because of the Fellnerness of K. When you shift it by sigma G, it almost stays the same. Okay, so you constructed things which are almost invariant and are kind of diffuse. They generate obviously subspace. So you prove that you have far at infinity, even in a free manner, independent manner, with everything you want, things that are almost invariant. So that tells you that this fixed point algebra, the fixed point has things, okay, that, a huge algebra, first of all, diffuse, okay, it's far from being strongly ergodic, your action on this, okay, and anything, for instance, these guys, the way we constructed it, they are freely independent with anything you wanted in N, that was my choice of U. So, but with things that are free independent of something, you can kill those elements by averaging with things in this fixed point algebra. So I proved that, given any finite set of elements, you can. So what this says is that the fixed point algebra, okay, can kill anything in N. You can find things in the fixed point that can kill by averaging anything. So that's what's saying that the fixed point algebra is trivial relative gamma. Incidentally, you only needed to prove that it's a factor, but that's very difficult because you cannot put your hands on the algebra. So you try to kill anything therefore, so that's exactly what it is. So that's that. I guess this we missed to get to this. So what I wanted to prove, because it comes nicely into this whole discussion, I would rather end, so straightforward, thank you. So it's because it's so related with the vanishing of the two cohomology, there is this really very simple observation. It looks kind of a fancy, lots of notations here. I wanted to emphasize that there is a way to reformulate Kahn's embedding problem, okay, almost in its full generality, not quite, through as a vanishing two cohomology problem. And it's the right place, of course, to say that. So here is how we do it. So let me state that we have not much room here, but Kahn's embedding conjecture, let me put it that way, so C stands for that, says that any II1 factor, did I call it, let's call it, yeah, II1 factor separable, so countably generated, there exists an embedding of it into R omega, or what's equivalent into the ultra product of n by n matrices. Okay, so this, it's trivial to see that the two are equivalent. Okay, so here is the sequence of trivial observation. First of all, so R, of course, embeds in R omega, any M embeds into M in its ultra power as constant sequences. If you take the commutant of R in R omega, this gives you a huge II1 factor, in fact, huge enough that its commutant in R omega is back to R. So you have this by commutant result, which is kind of easy to prove. Another simple observation is that any automorphism of R, we should have made this long time ago, there exists a unitary in the normalizer of R in R omega that implements it. This is trivial because you have, obviously, for n by n matrices, 2 to the n, so let's think of R as a limit of 2 to the n by 2 to the n. On any automorphism acting on some algebra, okay, if you have in the subalgebra in a factor, I'm sorry, so take any n by n matrices in any factor and take an automorphism. Then that automorphism restricted to that subalgebra, finite dimensional subalgebra, is implemented by a unitary. It's a trivial exercise. By the way, that's like one of the first things, I remember doing, when I started, in this subject. I mean, when I was 20 or 21, these were like the basic exercises I've been given, okay? So, for instance, this one, okay? And so, with that, you take the sequence for each bigger and bigger algebra, and you get, therefore, you have this approximate inerness of the automorphism of the automorphism of R. So, and also if you have another one that implements the same thing, okay, obviously they will differ by perturbation by a unitary in the commutant of R, right? So you have it unique, U theta up to this choice of multiplying with some unitary from the left or from the right. All this tells you what? Okay, it tells you that this theta goes to add u of theta, okay, restricted to R omega, okay, gives you a map, okay, from the automorphism of R to the automorphism of R omega, okay, and it needs just a little bit. By the way, that automatically it will also implement on R wedge R omega, because you have, it normalizes R omega. So, okay, and you can prove that it's in fact, actually that's the way I should have said it first. Okay, so it implements because it normalizes, okay, this normalizes U theta normalizes R. So it normalizes also R lower omega.
the comitant, or R prime intersected R omega. Okay? And I'm claiming that this initial theta is outer if and only if this theta sub omega is outer on this II1 factor. It's an easy exercise, okay? And if and only if this twiddle theta omega, which you also have it on this, is outer. So there is this, any free action therefore gives rise to a free co-cycle action sigma twiddle omega of gamma on this by just taking Adolf sigma, okay? So the corresponding two co-cycle, by the way, takes values here, is this thing. These are trivial observations. So what did we come to? So it means, by the way, I make another trivial observation. Any two copies, we mentioned that, you know, any two copies of R in an ultra power, any ultra power, are unitary conjugate. So it means that if I take any free action of a countable group gamma on the hyperfinite one, this guy, this cross product to one factor, in particular your L of gamma, okay, will embed, okay, into I call it CAE because that's for cons approximate embedding. I usually like to put, people in general put just C, cons embedding. It's true that cons embedding automatically it's an approximate. So you can read that way. It's an actual embedding in R omega. Okay, if and only if this two co-cycle vanishes. Of course, because, you know, if you, of course, if you can untwist the co-cycle, it means you have the embedding, and vice versa. Okay, if you have the embedding, then you put your R there, right? You move it with the unitary to the position of constant sequences. Then his normalizer, the canonical unitaries, are in this, it's one of those. It means they come, you remember, it's a unique choice up to the cocycle. So it means you, it's like, it means you untwisted that cocycle. So it implies conversely that you untwisted that cocycle. So you have this if and only. Okay, I wanted to, so it's a nice, cute, you know, really almost trivial. And by the way, I should point out that it's an observation I made, I think, in 2001 or 1999, 2000, 2001, something like that, at the crossover, that period. And until then, I was absolutely convinced that Con's embedding has an affirmative value. Now, after this, I changed 180 degrees, and I said, it's impossible. This cannot possibly happen. Okay? But then, you know, time passed, and I thought, well, you know, actually, so since then, you know, more and more frequently, I'm passing through being convinced it cannot to convince it can. So, right now I'm in a period where I rather believe it can, but okay, stop here.